Young Kim from Chemical and Biological Engineering Department. Okay, let me introduce the first speaker of this energy technology session, Professor Su. Professor Su received a bachelor's degree from the Virginia Tech, and he has also received a master's and a PhD degrees from the Pennsylvania State University. His current research activities are wind energy, energy efficient building technology, and the surface texture to reduce friction in cars and trucks, etc. Professor Su is leading the energy initiative for the School of Engineering and Applied Science. Before joining GW, he was at NIST, Penn State University, University of Maryland, and Northwestern University. Now, please welcome Professor Su.
Good afternoon. I know it's a long day, at least for me. Well, I'll keep it short. Talk about energy. And the issue of energy also tie in with the environment, about the Earth. And I will show you why we say that. The energy, of course, is the foundation of human society. And as such, you look at the population growth, it's very interesting. Since the discovery of petroleum and use, the world population jumped from 1.7 billion to 7 billion in just 125 years. And that's astounding, because once you reach 7 billion, the geometric progression will say we'll hit a limit at some point in time. And between 1980 to 1995, only 15 years, 445 million acres of forest land were lost because we need the land to build a house for the people. So, and then the rough estimate is, on average, every person adds about 20 tons of carbon throughout your lifetime. So you multiply by 7 billion, now you say, well, where does the carbon come from? It's very simple. So, well, we always talk about energy crisis. Actually, we don't really have an energy crisis. We have plenty of hydrocarbon we can use for the next 1,000 years without any problem. But the real problem is that we're really not certain how much oil that we have, and increasing demand for oil. And petroleum is the cheapest, most dense, and easiest to use energy. Just look at the population growth. So we don't really have an energy crisis, but we do have a petroleum fuel crisis pending very quickly. So we have to understand the problem before we can deal with it. So this is a projection from a peak oil study. Now, peak oil is a hypothetical modeling, and there's about 36 different models. And this is taking it as an average, and a lot of people object to this technique of modeling. Actually, it's quite authentic. If the data is based on each oil well in the world, its production curve and its decay. So what you're seeing is, up to this point, is all the actual oil well extraction production curve accumulated into it. The problem is predicting the future based on the past decay curve. Right? So nevertheless, I think that we can all agree from here to here, we have certain degree of uncertainty. Maybe plus or minus 10 years, 20 years, who cares? But it's going to go down. The fundamental truth is, look at it, is now we're going to see huge increase in natural gas production because of technology developed in fracking the shale oil. However, our liquid petroleum is hit the peak already and is going down. So from now to here, you can start to see that the oil production is going to drop very quickly. So this is the oil usage by end-use sector in the United States. And fundamentally, the transportation is 96% oil dependent. We basically extract all the oil in the earth, and then we burn it in the least efficient technology, which is only 30% efficient. When you come to think about it, it's pretty dumb. Let me put it this way. So Now, the world population of cars actually is increasing, and this is transportation of oil or consumption of world oil, and you can see about roughly 60% of all the oil goes into burn. At the same time, you have this vehicle growth projection, and you can see developing countries, industrial countries, you all shut up. So roughly by 2050, we'll have 3 times the number of cars. So the United States right now imports about 10 million barrels per day, which means total consumption is about 20 million barrels per day. And therefore, we are paying roughly about $1 billion per day, every day. And people wonder why we have economic problems. And the only reason U.S. still can sustain itself without going bankrupt is because everybody we import oil from turn around and buy our treasury bills. And if everybody stopped buying our treasury bill, the economy will collapse, no matter what. It's not an issue of federal spending. Actually, the issue is $1 billion a day is a huge number people need to worry about. So the real energy crisis, vehicle population goes up, petroleum supply shrinks by 36%, oil supply dropped from 21 billion barrels to 8 gigabarrels, so a 60% drop. And meanwhile, natural gas is booming, but the problem is we don't know how to use natural gas to power our cars and trucks. The only thing we're using natural gas is our bus. And you see this huge gas tank on top of the bus. How to translate technology and into our minivan and our automobile is a big issue. The technology is not there yet. So now, assuming current world average fuel economy is about 20 miles per gallon, the average fuel economy will have to be about 263 miles per gallon by 2050. So, right, gentlemen, you are just seeing the beginning of fuel economy drive around the world, no matter what you believe. You say, well, let's do electrification. So President Obama announced 2 years ago, we will put 1 million electric car on the road. Without checking with the Energy Department, and Energy Department go back and say, it's impossible, Mr. President. We don't have the battery production. Because lithium-ion battery is huge amount. The Tesla uses 1,000 pounds of lithium-ion battery. 1,000 pounds per car. Okay. The Chevy Volt is 400 pounds per battery. And you multiply by the number of cars projected by the average, let's say 600 pounds per car, you're going to extract all the minerals in lithium-ion, and you will never come close. So that is an interesting theoretical solution, but not a practical projection at all. So the consequence of this energy crisis that we're talking about is rapid change in transportation technology. In the next 10 years, you're going to see drastic change in the way we drive our car, in the way we purchase our car, and in the way the car is powered. Increased fuel efficiency, electrification of cars, hybrids, mass transit, natural gas power, all these things are logical conclusions. Unfortunately, we are not putting money in those areas. And it's kind of interesting because every country look at their near-term energy crisis, they have their own interpretation and own internal policy to worry about. The logical facts-based science and technology development is not there. Energy efficiency reduces consumption in all sectors of technology, buildings, ships, industrial, lightweighting, electronics. These things are the natural consequences of this energy crisis because we don't run out of fuel. Cost-competitive renewable energy generation, alternative technology to reduce CO2 on a massive scale, lightweight nanocomposites with self-adaptive properties that are eco-friendly and multifunctional. So these are the kind of a technological solution. However, we don't have the political will and the national will to pursue a logical conclusion. And the fundamental issue is that all the other hydrocarbons that we have, They are there, but they are far more expensive. So the cost becomes a major issue. So when we look at GW, we also have to select among all the possible subsets of solutions because we have to find our fit. So basically, we're looking at renewable energy generation, wind energy, which we look at material-based, cold spray, nanocomposite, cell repair, all based on economics. Solar energy, nanoparticle solar cells, because it's cheap. Energy efficiency, we're looking at energy efficient building technology, microgrids, on-door, multivariable analysis to develop the next generation of control programs. Fuel economy increase, we're looking at surface texture, surface treatments as part of our niche. Industrial technology, energy efficient computing, which is led by Professor Howie Wong. And low carbon energy, we still have to worry about nuclear technology. So that's really where the overall picture is not in a detail. So when we look at wind, the wind is about 30% higher cost than it should be. So the fundamental issue based on DOE is fundamentally we want to lower the wind energy cost by 50%. Therefore, it can become self-sustaining industry. And when we look at it, the analysis is saying that, well, we changed the material or the blade from thermoset composites to thermoplastic. We could save about 50%, 60% of weight. And we can also easily shorten the manufacturing process by at least about 1/2. So that's a logical solution, so why we're not pursuing it. Cold spray, right now in the US, most of the wind turbines move offshore on the Atlantic coast because that's closest to the population. The question now is transmission and also the blades in an open ocean has a very different environment because you're running into corrosion by seawater and erosion and also as well as biological attack. So the surface has to be treated. The question is the blade weighs about 100,000 pounds per blade and stretch out to about half a mile. Now the question is how do you treat it? How do you put coating on it? So the only logical solution is use cold spray. Your cold spray, you can basically make a giant spray gun and spray the whole thing without a chamber. So that's the direction that logically the next generation technology would need. Cell repairing agent for turbine gears. The turbines have a 10 tons of gears weight, very material intensive. And when you're on a land, it's very expensive to repair because you need a sky hook, you need 3 other trucks to lower the blade one by one, and then you repair the gear. In the ocean, that's 10 times worse. So right now, if the wind turbine, if you service it once every 3 years, you make money. If you service more than once every 3 years, you lose your shirt. In the ocean, the ratio becomes much more severe. You can't afford to service it once every 10 years, in fact, because the population density and the turbine, number of turbines is much smaller. So those are the issues. So we are looking at, can we develop a cell repairing agent for turbine gears that will make it a normal way of operating the gears at a service interval once every 10 years. So that's the kind of thinking that we have. And then the smart blade, biomimetic surface textures, actuators, and all this activity have a whole group of professors working on it. I just don't list their name, but this is just want to give you a clear idea what we're trying to do. So the gear pitting is very clear. So the issue is when you have once you pit, the question is how can you repair it? Our idea is we're using nanoparticle of metal. All gears are made of different metal elements. So the question is, can we use nanoparticle that will make and put a layer or monolayer of molecules that is the bonding strength is controllable. So now once we know it's controllable, we can put it in when there's a signal or vibration telling you the gear is in trouble. And at that time, now you can release a bunch of what we call micro-encapsulated particles at that time and go in and repair the gear. So there's an initial experimental data to say that is feasible. One of the key problem is, in order for you to self-repair, whatever the layer you form has to be harder than a substrate steel. Otherwise, it got wiped off. Right. So that's the area that we are working on. Surface texturing, you can put wide variety of texture on a surface. And we are looking at it. It's basically what we want to use the surface texture to control the individual properties. We think we can control the heat transfer characteristics. We think we can control the friction. And we think we can control a lot of things by tailoring and designing a surface that has the shape and size that is directional, both in terms of X, Y, as well as Z. Now, so far in our technology, we only think about surface, you just make it homogeneous, isotropic, without thinking about how can we change the direction of heat transfer, direction of friction, and the idea behind payment control. So we put in a different texture and run at different things, and you can see the friction we can control very well from a baseline. The multi-scale is necessary because we are thinking about, basically we want to design a texture, a pattern of holes, dimples, and grooves on a surface. And then some of it we do very shallow. Some of it we do very deep. What happens is now, when the contact pressure is very high, the shallow ones disappear because deform and disappeared. So now it depends on the depth of pressure, the surface texture keeps changing. And that gives you what we call smart texturing technique that will do a lot of things. So how does the texture work? In most cases, it's through cavitation. So you need a certain speed, certain low, and you can see in this slide, we basically make a transparent sapphire and carve out a specific texture, size, shape, and depth. And then we measure the fluid mechanics, and you can see here the gas bubble begin to appear, and that means now you have the pressure changes, it provides a lift force to reduce the contact stresses. So once we successfully demonstrate technology at the lab, then we start working with diesel engine companies, and so now we start texturing real big things. Before, we're talking about labs, we're talking about microlithography technique, 2 millimeter by 2 millimeter. And all of a sudden, this is well, about 1.5 feet tall and 6 inches in diameter. So the question is, how do you texture this thing? And then when you go into the engine, how can you achieve and make sure that your texture works? So we basically now go through our microfabrication technique and basically go through, make a positive texture on the surface, and then we basically pour a polymer film and peel it off. And this is, you see the pattern. And the size of this polymer film fundamentally only is limited by the size of the wafer. Right now we're using 8-inch wafer. But theoretically you can use 18-inch wafer. And this is a major breakthrough, and we filed a patent protection on it. Now it means that we can actually take any parts, bearings, any transmission, we can actually now easily and low cost put in a patent on the bearing steel surface. And once we do that, it provides a very low cost issue or production issue, because now this texture can be photoreflexively crafted on the bearing surfaces using electrochemical etching. And electrochemical etching on a large scale manufacturing production, it costs roughly about 1 to 2 cents per piece. And the time it takes to carve this thing is about, once you make the mask, is about 5 seconds. So it's very rapid processing. And once we get to that point, now we can see we need to demonstrate whether it works or not. So we actually use a simulator together with Cummings. We're basically using actual production ring and actual production piston. And a piston is also have a texture of what we call cross-hatched piston. So now we do a simulation, and you can see this is the baseline without texturing. Everything is the same. Now once you texture, you see the friction drops from 0.02. And you can calculate now, you can save about 60% of energy per stroke. And that is a lot. So right now we are thinking about working with Cummins and Caterpillar, and we are trying to go into now the commercialization. So now we transfer this whole idea into multi-scale, multifunctional surface design. In a lot of cases, we find you need to have a nanoscale features inside the micro scale and then inside a millimeter scale. Otherwise, it doesn't work because the surface, when you come to contact, actually is a multi-scale contact. So the contact mechanics also look at is a layer by layer contact and not just single two flat surfaces come together, especially when you control the direction and depth and profile and geometry. So once we put that down, and we can now pretty well, we can control the size and shape and depth. And then the question is now we're getting into a situation where contact stress is high enough, it will wear. So the question is how long it will last. Cummins posed us a question is, we design our engine for 1 million mile durability. We use your texture, can you guarantee that it will be still there at 500,000 miles? So we developed technology now using a very thin DLC film, and on top of it we also use a bonded chemical lubricants, and that so far has met that target. But still they say, well, that may not be enough. Maybe we need 1 million miles. So now we're still working on it. So discrete impulse and groove can be designed to bring bearing steel. And out of this now, all of a sudden, the whole door opens up because now we can use the texture to hide self-repairing agents also by creating a large dimple on the surface that will avoid shear force on the ships. So now all of a sudden we can now put things inside the dimple so we can do drag reduction, anti-fouling, anti-ice phobic surface design. So this is the active project we are working on these days. So let me shift a little bit to the buildings. Buildings consume about 40% of energy. So the microgrid of energy efficient building have potential to halve the energy demand. Total US energy used by the building is about 40% or 41 watts of energy. So it doesn't really cost that much if we can implement a strategy in which we enclose a microgrid. Inside the microgrid, all the house will be retrofitted. And in that case, we can halve the housing energy market. So that means we can save 21 watts. So that is the area. Now why do we want to go into this? Because fundamentally, this building area basically saying nobody wants to pay. The reason now is the condition is shifting is because Obama administration had recognized buildings, all the jobs stay in the US. So now they're pouring huge amount of money into it and now asking questions and soliciting ideas. So that's really where we're working in. And also the Energy Security Act and the Independence Act of 2007 mandates all federal buildings to save 30% energy by appropriating $90 billion 2 years ago. So the $90 billion is still sitting there, contract has to be awarded, and right now it's waiting to happen. So that's a huge market, so that's the reason why we're going into. So advanced buildings, you have a whole bunch of things listed, and you can read it. So we are now working on a variety of different things to look at how can we make the building smart. Okay? So microgrid, basically you say we link up a system in which we manage our own energy. When the grid, when we need it, we connect. When we don't need it, we become an island. And so that's the idea. So once you create a microgrid, you have an efficiency improvement. However, the problem is your building's still old. It doesn't make any difference. So the next step is we go in and retrofit all the buildings. Okay? So now we can potentially save at least 40% of energy for a microgrid. So these are big scales. So these are the kind of energy perspective. I want to come in from the top and tell you why we make the decision to choose what we do. Thank you for your attention.
Next speaker is Professor Ho Jang, Professor of Material Science and Engineering Department, KU. Professor Jang received bachelor's and master's degree from Korea University, also PhD degrees from the Virginia Tech. Before joining KU, he was at the Ford Motor Company as a research scientist and the Northwestern University as a postdoc fellow. His current research activities are tribology of friction materials, atomistic modeling and the simulation of nanomaterials, and the electrochemistry of batteries, etc. Okay, let's welcome Professor Jang.
Thank you for the kind introduction. I'm Ho Jang from Material Science Department. And I hope you still have courage and energy to pay attention to my presentation. This is the last one. I promise I will finish it within 10 minutes. And when I was asked to summarize what is going on in the research activities at Korea University, in particular for the School of Engineering, I looked through all the faculty members, what they are doing. And I was amazed that more than half of them are, in a way, related to the research on energy savings or energy generation. Okay, so rather than getting into too much detail of the individual research and energy, I'm going to show you infrastructure of the energy research in the College of Engineering, rather than getting into details with the beautiful pictures. So, I'm going to explain with the structure of how the energy savings and energy harvesting and energy related innovation is going on in engineering school with two institutions, with one individual interdisciplinary energy research activities, and I'm going to finish with the individual research groups. So we have two institutional bodies working on the energy. One is the Center for Energy Research, and the other one is Green School. And I'm going to start with the Center for Energy Research. The Center for Energy Research has a mission with R&D and training and infrastructure. And of course, R&D is the most important thing, and training students and professionals is the second one. And also we have some close relationship with the Green School, which I'm going to explain next. And this institution provide provide the domestic and international workshops by building an international network, and then also promote workforce and information exchange, and also they provide the collaboration and so on. And they also, one of the important things for the Research Institute is the support for the graduate students. They provide the fund for the international students to participate for the international conference. And also they encourage publication of the students, and also they provide incentives for the research related achievements. And also they provide the seminars by inviting renowned scholars from the world, all over the world, and also they do some services which is related to the research. And another thing the Research Institute does is building the network for collaboration. We have a university, industry, and national labs, and they do very good collaboration from the three different parties. And the second one is the Green School. Actually, the Green School is something new in Korea. and that is individually separated a graduate school program at Korea University. And one thing which is particularly interesting is this green school is closely related with the KIST. KIST is the Korea Institute of Science and Technology, which is about 3 kilometers from here, very near. And this is the oldest research institute in Korea and government-funded one. And they focuses on the converging knowledge and policy and technology to address energy and environmental problems. And also they train future energy environmental specialists to find the new solutions to sustainable growth of our next generation. And currently we have 7 full-time faculty members from engineering school, and also we have about 50 adjunct professors from the KIST. They provide 3 different technologies. First one is energy-related technology, and second one is environmental technology, and third is energy and environmental policy. So we have policy here, which is we invited from the non-engineering specialists for this program. And also we have need-based, voluntarily assembled faculty members to make a interdisciplinary energy research. We had 2 of them. One is the Green Campus Forum, which consists of 8 faculty members. We have a company, LS Cables and Systems, and also Township of Songbuk, which is a local government of this town. We both together, and this is a Google map of our campus. And at the time, we tried to make a very green campus. And then, we actually built the solar cell on the top floor of the engineering building. Also, the second group of the Hana scale was to build with the solar panel and also with the student gymnasium. And solar, the wind power also was planned at the time with a small, mid size and small size on the top hill of the mountain. And also we need a smart grid to manage and to provide the high quality electricity. And this program went on for 2 years. And then we had another interdisciplinary research activities, so-called Electric Vehicle Research Forum. At the time, we had 9 faculty members, and at the time, we had faculties from law school and also public administrations, because we needed some legal issues for the electric cars to running around the village. So we made a route for CO2-free on-campus shelter service from here, and this is our plan to make a charging station for the shuttle bus. At the time, we had a partner from the electrical vehicle company, Korean company, by the name of KTN at the time. This is the small one they donated us, and we wanted to make a test bench for electrical vehicle. And this program went on for 3 years. And also, we have individual research group. Well, there are many more actually working on the energy-related research, but I selected some of them who are really dedicated to the energy research. With the wind energy, Professor Kang is working in the construction of the wind tower, and I'm working on the speed control of the wind turbine. And for the solar cell and lithium batteries, and there are 2 people from the material science department. Dong-Han Kim is one of the well-known person in the solar program in Korea. And Yoon and myself is also working on the lithium batteries. And as Professor Su mentioned about, tribology is one of the efficient way to reduce the energy consumption, and also we have activity on the surface and tribology. And Lee from material science, and I'm also working in the tribology. And for the fuel cell technology, we have Sung-Han Kim from chemical engineering, and Professor Shim from mechanical engineering, and Kwang Song from chemical engineering. And for the smart grid, we have a superstar here. It's Gil-Soo Jang. He's one of the famous person in smart grid in Korea. And for the energy efficient building, Professor Kim is working to make a highly insulating the material using the polyurethane. And with this, I summarize how the energy research is going on inside of the College of Engineering. And thank you for your attention.
Right now, we are going to hear result of the discussion for separate breakout sessions. So at first, Professor Moon, could you report the result? Yes, sure.
Good afternoon. I had a discussion, very pleasant one, with Professor Olaras. We have many common research grounds for future research, and really, I am personally very glad to have George University professors to know that they're doing very fine research with high quality, and also we also do the same thing, so we can do a lot of collaborations in the future. Actually, what we like to do is we like to send students, exchange students, as well as send ourselves too. It costs money. That's the scheme we have to think about and have to figure out how to do. Okay. So one idea is just use our personal grant for the travel expenses and accommodations and so on, and send students, and then also we just go ourselves to have more discussions and so on. Another thing is actually we like to open yearly joint workshop in this similar common area, for example in fluid mechanics, because I also had another joint workshop with the German university, and then doesn't cost that much, but it helps a lot. Yeah. So this is really a joint good thing to do in the future. So what I can suggest is actually there's one model I learned when I visited University of California, Berkeley. I met the dean of graduate school, and then he told me that the UC Berkeley has a agreement with one of the fine French universities. I forgot, either École Polytechnique or UPMC. Yeah? And this money is not really huge. As I remember, it covers travel expenses and so on. So a few $1 million, I said. Sorry. But actually, they accept proposal from each universities, and then there's a review committee. So probably 1 year they accept a couple of proposal or three more. And then the university supports the funding. So there's some kind of seed money in the universities, between two universities. So I think that's a good model which can symbolize this collaboration between two universities. And so I hope we could have the same thing. Maybe Dr. Lee got interested in these things. Okay. That's it.
Okay, thank you. So next report is by robotics area.
Okay.
Thank you. My name is Hanso Ko. I've had two colleagues from GW attending this developing action items. So we have about 8 different bullets here. The very first thing is that we need to be able to have a better understanding of what we're interested. We realize that we are interested in each other, but specifically how we could do better is by perhaps exchanging research summaries. So that's the first thing that we're going to do in the next couple of weeks, is to exchange write-ups of, let's say, every student, every graduate students. We're going to develop, draft up research summaries of individuals with publication record, and send all that to counterparts in GW. And GW faculty will also do the same to me, and I'll spread all these materials to all other robotics related faculties at Korea University. We want to also develop a common application theme, because if you have a common application theme, maybe that could allow us to focus better and work toward move forward with a little more effectively. So what we are thinking of, maybe we're still in the process of thinking, but maybe one area of common area application is perhaps emergency response type of an area for, like, firefighting in high-rise urban firefighting, autonomous system performing search and rescue. Robotics system would be one possible topic. So if that is the topic that we indeed decide, then we're going to try to again exchange information. For example, I know that there are a number of different similar research activities going on with different umbrellas, research umbrellas by other schools in the States. Maybe counterparts at GW could, make a little bit of obtain, their ideas there, and perhaps apply similarly here for Korea. So that would be a great topic for the city of Seoul, by the way. So I think that's going to be a great area to start off. So as long as we have this common area, common application, we can move forward, effectively. Maybe that will force us, if you will, to be able to communicate more often. So in terms of communication, we could do it in terms, using maybe remote seminars, exchange graduate students, let's say over, especially in summer. We could also help each other on paper drafting and editing, back and forth, and that also could be a major, contribution from both sides. The other thing is maybe you could look for also some funded graduate student exchange program by NSF. There are a number of funding sources that I know. Maybe NSF might be one, ONR is another. So maybe counterparts at GW could look for those kinds of funding sources. At the same time, we do have like counterpart funding sources here as well. So we'll do the same in parallel. Number 6 is the co-advising of undergraduate students and encourage students to MS to PhD program. What this is about the undergraduate students exchange program, participating students who come to Korea University and vice versa. Korea University students attending at GW. If they are motivated enough to continue their study into graduate school, why not have the GW undergraduate students continue their graduate school at Korea University, let's say up to maybe master's degree, and then go back to GW for their PhD, obtain their PhD or work on their PhD degree program. I think that might be a good, linking all the components in a full circle. Okay, So that will allow maybe a little bit tightly coupled relationship between the two universities. So that's what hopefully we could do. So essentially, overall help to establish cross, what is it? Germinated? Is that the term? Is that right? Okay, the cross-germinated student pipeline. We could also, again, identify some funding sources for especially faculties from GW to come and visit, for example, like summer visits, which I think we do have, the cost is not very much. I think as I was speaking with them, costs seem to be very, very affordable. So I think that's something we can accommodate that here at Korea University, inviting GW faculties. And hopefully we could be invited by GW, right, as well, likewise. So anyway, so we've identified up to number 8. We ran out of time. We were escorted by somebody from here, so we ran down here very quick. So this is how, as far as we went, but I'm sure as we continue to exchange, communications, maybe we'll develop something more concrete. Okay, that's about what I have. Thank you very much.
Thank you so much. So next report is by Professor Ung Kim.
We also had a pleasant and exciting discussion, and we also found some common research interest. We talked a lot about research, common interests like flexible electronics or the optoelectronics. Interesting thing is we could be very complementary because Korea University is strong at synthesizing novel materials such as nanowires and nanoparticles, graphene and things like that. And George-Washington University is strong at physics, understanding things, and the device fabrication and application, things like that. So I think it could be a good, the collaborative party, complementary each other. So that's a good thing. And then we were also talking about writing paper together and things like that. But I think we can extend it to the exchanging student and joint workshop, and then maybe co-advising students and things like that as well. Okay, so that's it. I think we can be a good establish a good collaboration. Okay, thank you.
Okay, thank you. So the last report is by Professor Ho Chang.
I don't have a view graph, but Professor Su and we discussed about our future direction and what is the possible action list from this moment. And there are two different things, one for the students and the other for the research activities. And we agreed to share the compile of the area of research and contact points for those who are working for the research area, the energy research area, because we have so many different variety of backgrounds in the energy-related research. I think we have to share the information for the graduate students who probably can visit for the exchange programs. And also, we end up with the possible 3 different areas for the future research collaborations. The first one was the surface texturing technology, which to improve the fuel economy or the energy savings. And the second was the smart grid, which was, we both have a interested in. And also, the third one was energy efficient materials to save energy. And that's about it. Thank you very much.
Thank you. Thank you for your valuable report. And now I would like to ask Dean Darling to wrap up today's discussion and today's symposium.
Shall I take this one? Sure.
Well, thank you very much for asking me to wrap up. Before I forget, I would like to thank Dean Shea, especially for leading the effort here at KU. I also wanted to thank Associate Dean Zhang. I had many email exchanges with him, and he took care of many issues, and so I wanted to thank him very much too. I also wanted to thank Simon Lee. Simon has been the force that has driven this exchange from the very beginning. And Simon Lee, in case you don't know, is listed as #1 on the world's greatest hosts list. Everybody in the GW delegation would give him an A+++ grade for support of our visit, for taking care of us and treating us in the best way possible. And that also applies uniformly to Korea University. I've made several visits here now. This was an excellent visit today, and you always conduct these meetings in an astonishingly professional manner. It's really a delight to be here, and I'm very grateful to you. Very grateful to all the participants for putting together the presentations today. We were just joking, not really joking because it was true, that in conversation there is an English expression or an American expression which is drinking from a fire hose. What that means is that when the fire truck comes to put out a burning building, they have a very large diameter jet of water, and it's just like, today has been just like drinking from this hose, such an enormous amount of information. I think it's flowed out of your presentations and it's flowed out of the GW presentations. But I think what is evident to me, for sure, and I hope it was evident to you, is there is a lot of overlap. We are doing distinct things in our different schools and departments, but we are doing a lot of common things simply because your research is addressing the challenges that Korea faces and the world faces. Our research is doing the same thing, and by necessity, there has to be a significant amount of overlap. And on the basis that 2 heads, 3 heads, 4 heads are always better than 1 head, I think there is a lot of opportunity here. I want to thank the 4 persons who just spoke and summed up some action items. I think there really are some good action items there. And what I propose that we will do is we can take the lead on this, and it can be a little bit like a bouncing ball from one group to another. We will write up a sort of summary, a very short summary, a 1-page, 2-page set of what we consider to be the action items. We'd like to give that to you, and maybe of the several things that will be on that list, the 2 deans between us can pick on 3 or 4 priority items, such as the exchange of graduate students, maybe a summer faculty opportunity, and I think between us we can find ways to support those. I'm putting words in your mouth now, but I know that this is important enough to me and my school that we will certainly find some resources for seed support and so on to get exchanges off the ground. The trick is always the researchers themselves have to identify where there is opportunity, because research collaborations can never be imposed from the top. It just does not work that way. Research collaborations have to happen because the individuals see the benefit to themselves and their students and their programs of working with other people. And I think I've seen for myself opportunities there, and I believe you have on both sides here today. So let's move forward. Within a very short period of time, I will exchange information with Dean Shea, and then we can start this ball rolling. Today has been a delight. I want to thank you all again. And I'm hoping at some stage we may host this at GW. and all of you guys can fly 8,000 miles and enjoy 14 hours on the airplane. Seriously, it would be a good opportunity for you to visit. And I think the ideal time to do that would probably be once we get our new facility opened. It would be wonderful to have one of the first things that we host in that building would be a research symposium, number 3 perhaps, number 2 perhaps, between us in our new facility. Is there anything GW delegation thinks I've missed out at the moment? I hope there's nobody I've neglected to thank, but sometimes one puts the microphone down, sits down, and realizes, wow, I completely forgot to say something. If I have overlooked somebody or something, I apologize. Do you have anything to say, Simon? You want to add anything?
I'm going to save that
For the
photo section.
Okay. Okay. Well, on that note, I'll hand the microphone back over to you, and you did a fabulous job.
Thank you.